This is video 18 in the series of reinforced concrete slabs. In this video, we will deal with the strip method. We've seen that when we are using yield lines, you need some ductility requirements, because otherwise the formula of the plastic bending moment is not valid, because this formula is independent of the concrete strength. So this implies that the steel must first yield before the concrete is crushed. This ductility requirement can be obtained if the reinforcement ratio is between 0.15 and 1.5%. The lower limit, 0.15, that you can obtain when you put minimum reinforcement in it against brittle failure. So most of the time we will comply to this condition. The upper limit, 1.5%, that's when the reinforcement ratio is bigger than 1.5%, the danger of concrete crushing as first failure mode will be there. We can achieve this by, for instance, for concrete grade smaller than C50-60, you limit the compressive height X over D to 0.25. So this will assure us that we have enough ductility in the slab for greater grades of concrete. This compression height must be lower than 0.25. Considering this, then we see that when we are using the optimum height of the concrete at the design, then at optimum height the compression zone is 0.259 times the effective depth. So this means that to fulfill the requirement of ductility, we should only use yield lines when the effective depth of the slab is at least as large as the optimum depth. We will now have an overview of the plastic. In the plastic methods of calculating bending moments for reinforced slabs, reinforced concrete slabs, you can divide them into two main groups. The first one is the static method. It means in the static methods you will have a lower bound of the load-bearing capacity, and an example of that we will see is the strip method. The second group is the kinematic group, and in the kinematic group the load-bearing capacity is an upper bound, and as an example we will see the method of the yield lines. Now we will look at the strip method. In the equations from Kirchhoff-Lagrange, we have seen that the second derivative of the bending moments, that in fact this is the first derivative of the shear force, and it was equal to the load, the ultimate load. When neglecting in this formula, when we will neglect the torsional bending moments, then you have something like this. But this means that you can split it up in two directions. If you take the equation in the x direction, and you take one portion of the total load, and then you take the other direction, then at this stage you have reduced a two-dimensional problem into the summation of two one-dimensional problems. So it means that you reduce the problem of a slab into a problem of a beam. Let's have a closer look at the strip method. We've seen that taking a slab and you increase the load, the uniform distributed load gradually, then you will see that there will be yield lines which are there, and that the whole slab will divide itself in sub-slabs and making a mechanism until the all bending moments are completely distributed. Looking at this picture, you will see that in the middle the loads are carried for half in this sense and in the other half in the other sense. In this area, this load is carried in this way and this load is carried in that way. So, of course, this is only valid if A is smaller than 2 times B, otherwise you have a one-way slab. You can now identify zones or strips where the load is carried in a certain direction. So in this middle strip, the load is carried in this direction, and then in this strip, the load is only carried in this direction, and this strip in this direction. But in the corners, the load is carried away in the 4 directions. If you look at the strip at the yield line, you will see this. This means that now we have zones or strips in the slab where we can calculate the bending moment, and we can calculate reinforcement, and we place the reinforcement in those strips. So that's why it's called the strip method. So it's reinforcement in zones. Now we will have a look at section 1. In this zone, the bending moment is just a strip on two single supported or simple supported conditions. So the bending moment is QA squared. A is the span in this direction divided by 8. On strip number 2, or in section number 2, you will see this load is carried in this way and this in this way. But the load that is carried in this way is half of the load, because the other load is carried in the other way. So this is half of the load. And then the bending moment, when this is D, the bending moment in this strip in this direction is QD squared over 4. And then we have section 3. We use the same method. In the middle there is nothing. In this direction it's Q over Q. It's Q as load. Then the bending moment when this width is C, the distance C, then we'll have QC squared over 2. And then the fourth section, it will be QC squared over 4. We use, in all cases, we use the same the same formula from applied mechanics when there is a portion of the beam loaded over distance d loaded with a load S, and it's symmetrically, then we know that the maximum bending moment in the middle is SD squared over 2. And depending on S, if it's equal to Q or Q over 2, you will arrive at those formulas. For instance, if S is equal to Q and D is equal to A over 2, then you will have Q8 squared over 8. But we have now the strip method, but we don't know what will be the value of what will be likely the value of C and D in the definition of the strips. Well, we will have a closer look at it. We take the width C, and when you go up to the cross section of where the yield lines are coming together, this value V equals A over 2 when this is 45 degrees, so it's A over 2. That's one limit. The other limit is the point of gravity, so it's 2/3 of v. That's the other limit. And so we know we should take c somewhere between 2/3 and 1, or if you substitute for v, then you will see that the mean value for c between the lower and the upper limit is 5/12 of a. It's just an assumption. Another strip is also fine, but this is more or less the best option that we have. In the other direction, again, it's the point of gravity, it's 2/3 of v. So in the other direction, we'll end up with d equals to 1/3 of a, which is also logic. So now in the strip method and in the 4 cross sections, and we have now seen what is the value of c and what is the value of d, which is 8/3. So the portion in the middle that remains is just beta a minus 2 times this distance. Instead of b, I have changed it in beta times a is the same as the length of b. So it means beta must be smaller than 2. We will look again at the bending moments. The maximum bending moment for strip 1 is q8 squared over 8. In the bending moment for cross section 2, it will be q8 squared over 36. And for cross section 3, it will be q8 squared over 11.52. And in section 4, it is q8 squared over 23.04. It's just the formulas that we developed in the previous slides, and we just fill in the value of c and d and the value of b, which is beta a. Now, this is very peculiar because now for a rectangular slab, isolated slab, simply supported on all sides, loaded by uniform distributed load, well, all bending moments are independent of the second dimension of the slab. It's independent of beta. On the condition, of course, that beta is smaller than 2. So this is very interesting to see and easy to use in practice. This strip method has a large advantage. It's very practical and it is logic. We just must not forget to put the right reinforcement in the corners, because the strip method does not qualify for that. And we must not forget to put the torsion reinforcement needed on the top and the bottom of the slab. We can use the strip methods of 1 meter width, for instance, for creating supports for small line loads. And we'll give an example of that. We have a rectangular slab, simply supported on all sides. And suppose that we have here on this side a brick wall with a low line load. And we have a brick wall which is standing, or a line load standing, acting on the slab. This is a cross section, this is a slab, the support of the slab, and this is the line load on the slab. So how can we deal with it? We use a strip method. We are taking a strip of a width v. This is the red one, and we will reinforce the strip as if we are reinforcing a beam. And the loads on that beam is of course, the proper weight, then the line load P in kilonewton per meter, the mobile load or the total load of the slab in kilonewton per square meters, left and right of the line load. And then the width V, you can take 1 meter, or you can calculate this needed width, which is better. You take the distribution of the line load at an angle of theta up till the tension reinforcement. It means up till level D, the effective depth of the slab. The reinforcement in the direction of A will then be the bending moment is coming from the line load P, and P times it's kilonewton per meter on it's 8 squared over 8. And then we take the uniform distributed load Q, left and right. It means it is V minus S, it gives you the portion on the left and the right of the wall, times Q8 squared over 8. That's the bending moment. And the width V is in fact equal to 2 times cotangent theta D plus S. And when cotangent theta is 1, then you have 2D plus S. So it's quite obvious that V is then 2D plus S. And then you calculate the reinforcement for a beam with a height H and a width V and subjected to a bending moment MED. So this is how you can use the strip method for simulating a fictive support for a line load.